Welcome to Lecture 8 on an Introduction to Fertility and Crop Nutrition. This subject is part of the agricultural degree offered at North Melbourne Institute of TAFE, based in Australia. Please visit our website for further details on our subject, courses and educational products that we offer. This lecture is on an introduction to fertility and crop nutrition and is the first lecture of 3 in this topic. Please ensure you watch Lecture 7 on soil and agronomy before you continue with this video. My name's Dr. Nikki Cooley. Aristotle had thought that food of plants, like that of animals, was not simple, but composed of various combinations of the 4 elements earth, air, fire and water. Plants, however, get their food from the earth by the means of their roots, and this food is already elaborated when taken, which is the reason that plants produce no excrement, the earth and its heat serving them instead of a stomach. This concept was accepted for many centuries. We now understand that fertility is related to a selection of essential elements. In this lecture we will start our understanding of fertility with a snapshot on fertility and science. I will introduce the essential elements, along with several systems of classifications. You will learn about beneficial elements, the importance of ionic charge, and we will complete this lecture by introducing the law of the minimum. Soil scientists for many years have been demonstrating the relationships between fertility levels in the soil and plant tissue and plant yield. For example, corn and depth of horizon A level are linked to yield. The deeper the horizon A level, the greater the yield. This was shown by Al Kassizi from the Department of Agronomy ICM in 2001. Nitrogen uptake is linked to crop growth stage. This figure from the University of Nebraska illustrates this concept. From the FAO organization, data was collected to demonstrate the relationship between wheat grain yield and total above ground nitrogen at maturity in farmers' fields in Mexico. Experiments in 1999 were conducted on Norway spruce stands. These existed on sandy and nutrient-poor soils located in western Denmark. These soils were analysed for their exchangeable calcium, potassium and magnesium. Research here demonstrated that the more calcium you added, the more yield you could obtain. These are just some of the many experiments that have demonstrated the relationship between fertility, nutrients, soil, plant tissue, and plant yield. So let us start with a definition. All essential elements are by definition required for plant growth and completion of the life cycle of the plant. That is, from seed all the way through to seed. There are 3 non-mineral essential elements. These are hydrogen, oxygen and carbon. These are obtained from either the atmosphere or water. Other essential elements that adhere to the Argonne and Stouts criteria include nitrogen, phosphorus, potassium, calcium, magnesium, sulfur, boron, chloride, iron, manganese, zinc, copper, molybdenum and nickel. Other elements may be beneficial to plants. These have been recently cited as such, and they include such elements as silicon, sodium, cobalt and selenium. There are other elements that have been hypothesized as being beneficial elements, but to date have not been proven. This is chromium, vanadium, and titanium. Out of the many natural elements that occur on Earth, essential mineral elements and beneficial elements are not randomly scattered, but instead they cluster into several groups. This is demonstrated on the slide showing the periodic chart. You can see the essential elements highlighted in green, the beneficial mineral elements highlighted in yellow, and essential non-mineral elements highlighted in blue. Plant concentrations of essential elements may exceed the critical concentrations, the minimal concentrations required for growth, and may vary somewhat from species to species. Nevertheless, the table on the screen shows the general requirements for plants. This data is based on dry weight. Whether in mgs per kilogram or parts per million or percent, essential mineral data is always presented on the weight of the dry material of plant and not fresh weight. Fresh weight includes both the weight of the dry matter and the weight of the water in the tissue. Since the percentage of the water can vary greatly, by convention all concentrations of elements are based on dry matter weights. The first system of classification I'd like to introduce to you is based on the concentration or amount found in plants. There are two groups, the macronutrients and the micronutrients. The macronutrients include nitrogen, potassium, calcium, magnesium, phosphorus, and sulfur. As you can see, their concentration occurs between 15,000 and 1,000 mg per kilogram. This varies between 1.5% and 0.1% of the plant's dry weight. The micronutrients are found in lower concentrations. The micronutrients include chloride, iron, boron, manganese, zinc, copper, molybdenum, and nickel. Are the macronutrients more important than the micronutrients? This terminology could indicate this, but in fact they are not. The relative importance in all cases is not linked to their amount found in the plant. Some essential elements are required in large quantities, while others in smaller amounts. Many of these essential elements are found in sufficient quantities in soils, and no amendments are required. The primary nutrients is another form of classification. The primary nutrients consist of nitrogen, potassium, and phosphorus, and are required in large quantities. All other nutrients are called secondary nutrients. This classification is based on how much of the nutrient you have to add to the soil. The ability of soils to supply secondary nutrients to plants indefinitely is subject of the law of conservation of matter, and this is therefore dependent upon nutrient cycling. Continued crop removal of calcium, magnesium, and sulfur requires replenishment, just as surely as primary nutrients, but most likely less frequently. Calcium and magnesium are often supplied by mineral weathering, either of natural soil materials or of agricultural lime or ground limestone, which can be added to the soil. Sulfur is often added to the soil as either atmospheric decomposition, which is associated with air pollution, or as impurities in fertilizers, particularly common pea fertilizers. To demonstrate that the classification is more responsive to soil ability to supply nutrients than plant requirements, It should be noted that plant requirements for calcium, a secondary nutrient element, is greater than for P. Calcium is found as a principal exchangeable cation in most soils, and an important soluble cation in the soil solution. Phosphorus, on the other hand, is only slightly soluble in most soils, and many soils, particularly those that are either acidic or alkaline in nature, have the potential for causing phosphorus deficiencies. It is important to have some understanding of the basic chemistry around nutrients. All but one of the essential nutrients is absorbed by plants from either soil solutions or nutrient solutions that are either a cation or an anion. Cations have positive charges, while anions have negative charges. Cations and anions may differ not only in the sign of their charge, but also in the magnitude. 3 is very strong, while 1 is weaker. In the table on the screen, the essential elements are listed in their approximate order of critical concentrations, from greatest to least, from top to bottom. Almost all elements are taken up as charged ions with charges of +2, +1, -1 and -2. Absent are all the organic compounds of the nutrient elements, indicating that all organic fertilizers must undergo mineralization of nutrients to become available to plants. Nitrogen may be taken up by plants as either an anion, NO3 nitrate, or a cation, NH4 ammonium. Plant preferences for nitrate or ammonium are species specific and are usually related to the natural environment of the species, with plants adapted to bogs or marshes, cold or acidic conditions often preferring ammonium, and most other dryland species prefer nitrate N. The ionic charge of the orthophosphate ion, whether it is H2PO4 or HPO4, is dependent upon pH conditions prevailing in solution. Iron can be found as either iron 3+ or iron 2+, with a difference in redox state as well as ionic state. Evidence exists that mandatory reduction of Fe3+ to Fe2+ is an essential part of the uptake of iron in many plants. Interestingly, several elements are absorbed as compounds called oxyanions. These are ions composed of the elements surrounded by 3 or 4 oxygen atoms, giving a net negative charge. Also of interest is the fact that several elements are taken up in different forms. Justus von Liebig, who was born in 1803 to 1873, was a German chemist who spent the early part of his accomplished career as a pioneer in organic chemistry. He turned to what is now called biochemistry about 1838 and first published on agricultural chemistry in 1840, and made numerous significant advances and engaged in extensive fruitful debate with other researchers in the field. Liebig made great contributions to the science of plant nutrition and soil fertility. As a result of a millennia of practical experience of farmers manuring fields to improve fertility, many early chemists thought that the principle of vegetation, the essential nutrients needed for plant growth, were organic in nature rather than mineral. Liebig essentially debunked the humus theory and made a scientific case for plant requirements for mineral elements from the soil, carbon from carbon dioxide in the air, and hydrogen and oxygen from water. Liebig thought that plants derive most of their nitrogen content from the air as well, which is somewhat correct for legumes but not true for other plants. Liebig developed the first mineralized fertilizers applied to replenish nutrients removed from the soils by crops, and clearly saw mineral fertilizers as a part of sustainable agricultural practices. He introduced the law of the minimum. This states that yield is proportional to the amount of the most limiting nutrient, regardless of which nutrient it is that is limiting. If the nutrient deficiency is supplied, yields will improve to the point where some other nutrient is needed in greater quantity than the soil can provide, and the law of minimum would apply in turn to that nutrient, and so on. The image on the slide illustrates the concepts behind the law of the minimum. The most growth-limiting nutrient will limit growth, no matter how favourable the nutrient supply of the other elements are. For example, a deficiency in iron or manganese, most common in soils containing calcium carbonate, can severely limit plant growth in spite of adequate P, K and N. This brings us to the end of this lecture on an introduction to fertility and crop nutrition. I hope that you have understood the scientific principles of fertility and crop nutrition that have been talked about here. You should be able to describe and classify essential elements according to either their relative concentration in a plant or their need to be added to the soil environment. We introduced not only essential elements, but beneficial elements. We briefly looked at the chemistry of nutrition with respect to ionic charge and that importance. And we ended this lecture by learning about the law of the minimum, an important concept that should be applied in agronomy.